Okay, so I want to walk through an old exam question, and here it is. We're looking at exam 3 from 2013-14 fall, and specifically we are looking at question number 2. Okay, so this is an interesting question. It actually combines a couple of different topics from the course. One of them is obviously involves Hermitian stuff, right? And the other topic that it combines with, I'll reveal in a couple of minutes. So first of all, it does present pretty explicitly as a Hermitian kind of arithmetic problem. So it asks us to compute the Hermitian norm of this vector W1. Now here's our definition of Hermitian norm for the purpose of this question. And here's the W1 vector, right? So straight up calculation. This W1 vector, here's its components, right? You can see those here. That's the first vector. And of course, then the second vector in that the Hermitian dot product here, you can see is the conjugates right there. And then the Hermitian norm is the square root of that self-Hermitian dot product. Okay. All right. The arithmetic to be punched up there. All right. Then the next thing the question wants us to ask is to divide W1 by its, we just computed Hermitian norm. Okay. So that's easy. Of course, just dividing by 6. Nothing to it. Okay. All right. Next, compute another Hermitian dot product. And well, okay, so direct calculation. The components of W1 are there. Oh, excuse me, V1. Excuse me, V1. V1. The components of V1 are there. Don't forget to divide by 6. And then W2. Right. Let's clear here. V1 is that. W2, its components are right here. Don't forget that in the Hermitian dot product, again, reminder, we conjugate the vector on the right. Okay, so again, a bunch of arithmetic, not that bad, but punch it up and there's an answer. Okay, so far it's been just arithmetic, following certain formulas. You're going to know what the Hermitian dot product is and follow the new given formula for Hermitian norm. So the next part looks a little bit weird. It asks us to show that this thing here is always 0. Weird. Now, this is just a brute force calculation. We're just going to explicitly do it. Notice that this is a Hermitian dot product. Hermitian dot products, right? We can distribute. So first the W2 and then minus, and then all of this business over there. So that's just distributing. Again, that's a known property of Hermitian dot products. A scalar on the right-hand side of a Hermitian dot product, that scalar will factor out with a conjugate. And again, that's one of the little tricky bits about Hermitian dot products. They're not, linear in that usual sense. There's this modified scalars factor out in this kind of, conjugated sort of way. So that's a little weird. Okay. And of course, that scalar that we're pulling out, that scalar itself was already a conjugate. And so thus we get a conjugate of the conjugate. Conjugate of a conjugate is the original number. Said differently, those cancel. Okay. All right. So a little bit of algebra, point being those cancel. This, of course, is 1. V1 we designed to be a normalized vector. So it's already been divided by its own magnitude. So its norm is 1. And therefore we have this minus, well, itself, which is 0. Okay, so straightforward calculations, really plug and chug so far. What's going on? Why are we doing all this? What you might notice is that some of these formulas look familiar. You might notice that if we go back up to part A real quick, dividing a vector by its own magnitude, right? That's normalizing. Where have we done normalizing before? Well, I guess we've done it in several places, but we've done that in the Gram-Schmidt process. Here, commuting a Hermitian dot product of a newly normalized vector with a second vector, right? That's very much smacks of what we did in the Gram-Schmidt process. And then down here, again, the analogy continues. We're taking this newly normalized vector and subtracting some carefully crafted multiple of it, right, from another vector. Well, this is exactly sort of the structure of the Gram-Schmidt process of sort of straightening out. I mean, in the Gram-Schmidt context, we did this because we wanted to make sure that to whatever extent W2 pointed in the V1 direction, we wanted to get rid of that. So what we got rid of in the normal, regular old Gram-Schmidt situation, what we got rid of, what we subtracted off, was the extent to which W2 points in the V1 direction. So that this is, well, we're not sure what to do with, I mean, is that what's going on here? We're not clear, right? Because this is Hermitian dot products and stuff, and what's going on with this conjugate here, etc. But notice the result of this calculation seems to suggest that this is the right way to do it, because after having subtracted off this much of V1, right, this must be the amount that W2 pointed in the V1 direction, because what's left over after subtracting it is orthogonal to V1. So we must have subtracted the extent to which W2 points in the V1 direction. So now none of what I just said there is really essential for answering part C, but that's kind of that's the eyebrow that was supposed to have been raised, and that we were hoping students would get out of this. And where that becomes useful is then in part D. So I ask for some vector V2. Right now, if you've noticed the Gram-Schmidt analogy, then you'll sort of realize, oh, yeah, that's the, right, we fix the direction, et cetera, and then we normalize, and this is our second fixed vector a la Gram-Schmidt. And notice that the features that it's supposed to have are exactly those. I want it to be normalized. Cool. And I want it to be orthogonal to the first fixed V1 vector. So really, without actually coming out and explicitly saying it, what part D is just finish the Gram-Schmidt process. Well, finish this Hermitian sort of version of the Gram-Schmidt process that we sort of noticed in part C that we've inadvertently been doing. Okay. All right, so that is where we go from there. We take this thing. This is the vector that's left over when I subtract off the what you might want to call the V1 part of W2. So this is the vector then that is, well, it's already orthogonal to V1. And to normalize it, I just take that, take that vector x2, I'm going to call it, per our pattern from the notes. I take that vector and divide it by its own magnitude. And that is going to do what we want. The fact that we're dividing something by its own magnitude makes its Hermitian norm equal to 1. And we've already confirmed that this inner product is 0. And well, this inner product is a scalar multiple of that. I mean, it's just the only difference is we've divided the second vector by a scalar, and so still 0. Okay, so get that and that as argued here. Okay. All right, so that's the big idea of this question. I wanted students to, I mean, you might say the first half or so of this question is just computing arithmetic. Then the third fourth of the question is making a sort of an algebraic argument using algebraic properties of this of the Hermitian inner product. And then the fourth part is, to check and make sure that students have noticed that this isn't really just Hermitian algebra problem. This is a Hermitian algebra of a Hermitian Graham-Schmidt process. That being the realization of where you should plan to get this V2 vector from. Okay, so I think this is a nice exercise. By the way, if you're wondering, where does this conjugate bar come from? One could argue that maybe it would have been just as good to rewrite the x2 vector. Instead of writing it like this, we could equivalently have called it W2 minus W2 V1. No bar necessary because I've switched the positions of those vectors, which does effectively conjugate it. So we could just as easily have written it like this. Looks a little bit more elegant that way. And so maybe you have a preference for that. I wrote it this way in the question to kind of make the algebra, the Hermitian algebra, a little bit more interesting. But in practice, probably a little bit easier to write it this way. Okay, hope this has been an interesting and useful discussion.